short meditation. I want you to focus on your breathings. Okay? You don't have to close your eyes if you don't feel comfortable with it, but it will help you. Just notice 3 very, very soft breathings that you take, the best breathings that you've taken this day. And after you finish these 3 breathings, take another one. And with this one, say thank you. And I want you to thank for 3 little things. The first one is to thank someone that gave you something during this week. It could be either something physical or something more not fully spiritual. For example, a good explanation that someone gave you. You could also thank this person for giving you something. The next thing that I want you to thank for is to thank for yourself. Think of something that you've done that you can thank for yourself for it, for a decision that you made, for a present that you bought for yourself. Thank yourself for something. And the last thing that I want you to thank for is something that you never thank for and you find as an obvious thing. You can thank for the fact that you're sitting in this class and we are studying and not fighting. Or something that is obvious for you, that you have enough money for your food. Or just for the fact that you have friends. Or that you're living as a typical human being and you don't have too many difficulties. Just thank for something that you never thank for. And with this, I ask you to take one last breath. And now you can open your eyes after that. And now we are going to start the recitation, okay? You missed everything. We just finished. Okay, so thank you very much for the cooperation, and I really hope that it will just help us to make this much more fun and joyful than previous recitations and classes. Okay, great. Thank you. Okay. So on Sunday, I started the topic of filters that I thought that will probably take us more than one recitation. And just to sum up, we were talking about 2 types of filters. The first one is called the spectral, is based on the spectral response. So we build the filter based on what we see in the spectrum. And the other possibility is to create it by something that is called systems, which are FIR and IAR. Okay, and these are digital filters. And then next, I wanted to go on and talk a bit more about what systems are, and I gave you a few definitions that we use. And with this in mind, all the filters that we are going to talk about now are filters that are designed by the idea of systems. Okay? Yes. So all of our filters, we want to know what exactly are these kind of filters are doing. So, for example, maybe I'll start just with a number. Okay, let's see this filter over here. This is a filter that you should already know because we were talking a lot about it. This is the convolution filter. So let's see what it says over here. So we have a filter called FIR. In a minute, I'll say what is next. And this one takes an average of the last n samples. It averages them and then tells you what was the average, okay? So you know it already from convolution, right? Because convolution is just about averaging causal window of convolution averages the last n samples, okay? And like with the big N. And then we can write it as just an average of the last specific samples given in the filter itself. And now, 1 minute. If we want to know what such a filter does, we want to say what happens when we take this filter and put it on our data. When we do so, it's like convolving with something. It's like multiplying in a convolutional way with the data. So for example, if you want to know what exactly this filter is doing, we take an impulse response, which means that we put in the filter a signal which begins with 1, and then there is a bunch of zeros. And if we put this 1 and bunch with zeros here, and the n equals 4, this will create the output of 0.25 for four samples. Is that clear why? If I take 1 and I put it here, okay, the average of 1 and all the filters were before it, the 4 filters were before it, before 1 equals 0. So the average is 0.25, right? If I take 0, the second one here in the impulse response, I put it also here in the system, then the output is 0, 1, and what was before, which is again 0, and this is again 0.25. Okay? And also for the third one and the fourth one. And then when I go to the fifth one in my signal, then I need to average across all the 4 indices that were before this one. So let's see if I'm looking at the fifth 0. Right. So if I'm looking at this fifth, the fourth 0, which means the fifth index, then I count 1, 2, 3, 4. All of them sum up to 0. And when I define 3, 4, it's 0. Therefore, here it will be 0. Okay, so an impulse response is like taking a function that is a delta function, which begins with 1, and then you have zeros. You put it in the filter, and you see what happens. Okay, and now let's see it more formally. Yes, Amit. Yes, yes. Ah, sorry. Yeah, it was a great question, and I'm sorry that I didn't answer before. So this just means the average across last n samples. What is the size of your window? Right? So, yes. And the small one is the index. Oh, okay. Is the index that you're calculating for. Okay. So now let's see this idea. This was just a numerical example. Let's see it more formal. So what we are saying is that we know that each linear system can be described as a linear multiplication of the input with the system constant, okay? So we saw at filters that we know that the relation between the frequency domain and the time domain is going from multiplication to convolution or from multiplication to convolution and back, right? So now what we can do, we can design a filter as a convolution of the signal in the time domain. Was that clear what I just said? Okay, let's try it again. If we want to filter a signal, which means that we want to take off specific frequencies, then the easiest way to design it is to use the frequency domain, right? And then we're saying, I want to have this frequency, but I don't want to have the others. And when we're doing such a thing in the frequency domain, we are multiplying the spectrum of the signal by the filter. But we know from math that multiplication in the frequency domain is like convolution in the time domain. Is that clear? Okay, so there is a relation. Convolution in the time domain is like Isal didn't talk about that, didn't show you the proof, the mathematical proof, okay? So in the frequency domain, convolution becomes multiplication. And also, if you have multiplication, this becomes a convolution. Okay? This is due to the way that the frequency domain works. Therefore, one way to filter a signal is by multiplication in the frequency domain, and then I can say that I want to take spectrum to multiply it by this function, which will initiate zeros for all the unwanted frequencies and will leave in only the frequencies that we want. And another way is creating a convolution window in the time domain. And this is what systems does, okay? They ask themselves, what is the convolution that I want to make on my signal? Yes, Priscilla.
And then the convolution, the signal, the loss signal, and like, what is the other thing you're calling?
Sorry, I was a bit remiss. Please ask again. And then the convolution, yes.
The convolution. Like,
Yeah, this will result in multiplication in the frequency domain.
But meaning like, if you want multiplication, so if you're doing a filter in
Yeah.
the frequency domain, the convolution, the equivalent convolution is with what kind, like what function?
So this is exactly what we see now in systems. So I start with the basic idea that, for example, I'll show it from the previous. So let's start with the one that we already proved in the last recitation. So when we see here, right, this bandpass filter, which means that I want to have only a specific bands in my data. I don't want to look at all the others. Then what I'm doing is that I'm convolving in the time domain. I'm convolving my signal with this kernel, okay, with a sync, okay.
Transform of the filter.
Yes. So yeah, so what we are going to do is that if we have the signal and this is multiplied by f over here, or this is convolved with the f over here, then it goes to the multiplication between the two. Okay, this is what it means. So one way is to design the filter over here and then see how it affects the time domain. And we spoke about it on Sunday, that it creates ripples. When you work through the frequency domain, you'll always have ripples in the time domain because of the fact that the transient change in the filter creates the ripples. And this makes a problem. So another way is designing your filter when you go from the time domain. And you ask yourself, what do I want to do to my signal in the time domain? Okay? So now let's see. So we say that when we create a system, we want to make a convolution. This is the formula for convolution, and here what we can see is that we have a representation of how our convolution filter will look like. Okay. So, sorry, this is not this one. I meant. No. Sorry, it's not what is written. What is written here is the following. Sorry. So we have, when we design like this, we can design the filters in two ways. The first one is called FIR filters, and the second one is IIR. What is the difference between them? The FIR takes as an input only the signal. Okay? It is designed in a way that it looks only at the signal. The IIR takes as an input the signal plus the filter before. Okay? So this is what you see here. That over here, if I want to know what the system of FIR does at this specific point, I take a polynomial. This is what is written here. These are different coefficients of the polynomial multiplied by the previous samples, one for each one. And this is an FIR filter. But over here, we see something different. Over here, we see an IIR system. And this one looks also at the previous points of the signal, but also at the previous results of the filter. Okay, so let's see. It will be more clear when we see the numbers, okay? So here you have, in the text, you can read about the differences between them, but I want us first to see examples and it will make it easier to look at. So if we want to know what does this filter do, this is an IIR filter. You see that this one, for each sample, it takes the exact same sample at the signal and takes off what was the response to the previous sample. Do you see that? What was the filter of the previous filter? So let's see what happens when we take this impulse response. So we take this signal. Impulse response is signal. So we take the signal of 1, 0, 0, 0, 0, and we put it here, and we want to know what will the y be. Let's do it together. So y of 1 needs to be x of 1, x at the first sample, minus y of 0. X of 1 equals 1.
Right.
The first sample
Oh,
here,
it comes
x,
zero.
yes,
Oh,
thank you. So the first sample here is 1, and the previous sample of y, there wasn't any, therefore we write here 0. So 1 minus 0 equals 1. Let's take the second sample. So we take here x at the second sample minus 1 y at the previous sample. X, the second sample is 0, great. And the previous sample of y was 1. Therefore, this one is minus. Y of 3 equals x of 3 minus y of 2. X of 3 equals 0. Y of 2 equals minus 1.
oh.
Right? This one. I take the previous one. So this one equals plus 1. So you can see that this is a filter of oscillation. It oscillates between 1 and minus 1, 1 and minus 1, 1 and minus 1. So this is like convolving my signal with an oscillation with a very, very fast frequency. This is the idea of an IAR. I can represent an infinite kernel for the convolution. Do you remember what is kernel of the convolution? This is this part, what I multiply by in the convolution. Okay? Yes. Because it changes between 1 and minus 1, like I mean the fastest way to change within each sample. So this one, if you want to draw it, it will look like from here it's 0, so you have 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. So you convolve by this infinite kernel. Okay? Let's have another example. This is called the exploding impulse response. In this one, the filter takes the current sample and adds the previous sample doubles. Okay, do you want us to do this again with the exploding one, or is it clear? So let's see, in this one we need to write here plus 2 times y0, so this one will be still 1. This one will be x of 2 plus 2 times y of 1, so this will be 2, right? So this one is 2. And here, it's plus 2 times the previous one. The previous one was 2, therefore this one is 4, so this one equals 2, 4. Okay? I think there is a mistake here. It shouldn't be 6. Sorry, it should just be 1, 2, 4, 8, and so on. Okay? So this is an IAR filter. It takes into account not only the signal, but also what was previously done in the filter response itself. Okay? Now let's see an example. So we are asked to draw the impulse response of a IAR filter that is defined by y of n equals half of the previous output of the filter plus the current sample. Okay, and in a minute we'll calculate the FIR. Okay, so I'll go out of the share screen. Close this one. So that also the Zoom people can see it better. Okay, so y of n equals half of the previous one plus the current x of n, and we take the impulse response, therefore it's the impulse is x of n is 1, 0, 0, 0. By the way, Austin, is that studied also in engineering? Yes.
Yeah.
Yeah, right? Filters are also heavily studied in engineering. Yes. Okay, so let's see. What does y of 1 equals to? So this is half of the previous response plus the current x of 1. This one equals to 0, and this one equals to 1, right? So this one equals to 1. Y of 2 is half of the previous one plus the current one at x, which is always with b here is 0, and here it's 0.5. Great. Therefore, we can deduce, do you already see the pattern? Y of 3 will be 0.25, right? Quarter. Why? Because we double each time the previous response. So what we see here is that what exactly is this filter? What is it doing? So we see here a series, right? An infinite series that each of, let's just see. Each one of the members of this series equals to 0.5 powered by n minus 1, right? Okay. So what do we know about infinite series? Some of them converge while others are not. Does this one converges? Ah, you're looking at the series itself. Okay, sorry. I meant to say the sum of the series. Okay. So remember that, okay, why did I ask you about the sum? Who could tell me about the sum? Because what did we just say that a filter does? It's a convolution, right? So if we want to have a convolution, what should we do? Exactly, convolution is like averaging, therefore we need to sum before. So we want to ask ourselves, is there any behavior of this series while summing up? So the summing up of this series converges or not? If I take 1 plus half plus 0.25 and I add more and more, will this converge into a specific number, or will it go to infinity? Right, and what is the number, by the way? 2, okay? So this one converges to 2. So in the second question, we say that we are asked if we can replace this specific, I'll show it again. So in the second question, we are asked if we can calculate an equivalent FIR filter. You see, it's over here. That will give an equivalent output with an impulse response error less than 10%. So how should we do it? So we need to do the following. We need to find what is the pattern of summing up so that we can decide, instead of taking the infinite IAR, taking just part of it and replacing this part with an FIR. Was that clear what I just said? So I say that we have here an infinite numbers in the series. So we have 1, half, quarter, 1/8, 1/16, and so on. And when we want to replace the IAR by the FIR, we need to think what part of this, for example, I can take only the first 5 of them. And when I take them as an FIR, which is a finite impulse response, then I can multiply by this convolution window, and it will give me about the same. Okay? So this is exactly the question. what should be the number of the convolution size that will give you about the same for 10%, less than 10% error, okay? So let's see. Yeah, so instead of taking the infinite one, I've just taken, for example, only the first two. Okay. So again, we say that, let's look again at this one. Maybe it will be more clear. So we have here the IAR. So we said that this IAR is like convolving the signal with this convolutional window, right? So what we want to do is, instead of taking the full convolution window now, we want to take just part of it and have something like the convolution over here. You see over here, we have a finite response, and we want to take some of our IAR response and use it as a filter, but this one is a finite one and not as an infinite one, and create about the same effect of the filter. Okay? Yes. Exactly, yes. This is called the, yes, the impulse response. Right, so let's see over here. So as we said, this is the series of 0.5 powered by n minus 1. And we know that each partial sum of this one equals to alpha over 1 minus r. Alpha, r, and k are given by this. So over here, the alpha is 1. Do you understand why? The r is 0.5, and k is n minus 1. We just take the formula, and we assign the different numbers in. So in this case, 1 over 0.5 is 2. Okay, now we need to find FIR, in which its sum is bigger than 2 multiplied by 1 minus 0.1. Right? Because 10% mistakes means that if we multiply by this, it will be bigger than multiplied by 1.8, because this is 10% error. Right? So far, so good. Let's finish, and then I'll just repeat whatever is not so good. So what we need to do is, we can check how many members from the series we need to take in order to describe the series, so that when we multiply by them, it will be bigger than 1.8. So I just start by writing the first 4 members, okay? And then, right, sorry. So that when I sum 1 plus half plus 4 plus 1 over 8 plus 4, sorry, plus 1 over 8, all of them together are bigger than 1.875. Therefore, this is the finite filter. Okay? So, was that clear what we've just done? Please tell me what is not fully clear, because this is a very important question to go on with. Yes. Okay, so you say that you have an infinite numbers. So you start summing them one to each other, so that the sum will be bigger than 90% of the full sum, right? So 90% of the full sum is 1.8. So if you take 1 plus half, this is 1.5, plus quarter, it's 1.75. And if you have the 1/8, so it's 1/875. So over here, this is enough to create about the same response with an error of less than 10%. Yeah, so in the answer, we took the first members, and when we want to create the same first input response, this is the way to do it, right? So for the first one, I take the current signal. For the second one, I need to take half of the previous one. For the third one, I need to take a quarter of the first one, right? So this is why we see here that all of them are taking the first one in the impulse response. Okay? And not something like the previous one. Right? Was that clear? Yes.
Multiplied by 1 times 0.1.
Okay. So let's see over here. Calculate an FIR filter, which will give equivalent output with an impulse response error less than 10%. So we have a measure of how wrong are we in the FIR, because this is infinite. I can also stop here or here. So I need to decide where is the right place to stop. So less than 10% means that the sum of these elements will be almost as will be 90%.
Yes. See you
At least
at we can go to the pancake
of the
if
full
together.
sum, right?
Bye.
Yeah. So 90% of the full sum is 1.8, right? The full sum is 2. So 90% is 1.8.
Exam for you,
Yes.
but the center not closed down.
Right. So I say that over here, you need to decide what do you write as a BR just asked. What to write over here in the brackets. Right? So in the first one, you just say, and how do you create half for the second one? You can take the first number. You understand that? Zero, exactly. So you still need to take the one at the previous part of the signal. So this is f minus 1, the previous one. And to create the quarter, you need to take again two times before, right? So this is how you decide what to write here in the brackets. Okay. So the impulse response will always be 1, 0, 0, 0, 0. So if you want y of n to be 1/2, quarter, and 1/8, we understood why we want these first 4 members, right? So how do I create this? By this. So I go to the first one and I just copy it. And I don't want to edit anything. So I write here nothing in relation to this one. And I want to create half at the second one. Half of the second one has to take the first one here. So it needs to be related with n minus 1 and multiply it by half. And the same logic for the third and the fourth. Right? Okay. Nice. It's really nice to see your eyes shining again. I thank you for that. Yes.
I remember I said something. This one.
So yeah, the IAR. So this is just about, I think. So here in a minute I'll talk about it. I just wanted to give another example. Okay. So we see here. I don't want you to see the the answer, yes. So this is another example from exam 2007. We have a filter described by its impulse response y of t equals to x of t plus the y of t minus 1. So, is this one an FIR or an IIR filter? Great. Why? Right. It's also in relation to the y and not only to the x. And so this leaves us with C and D in the exam. So which one is the right one? In this one, it is written that it is possible to create an equivalent FIR filter. And in the second one, it says that it is impossible. How should we decide if it is possible or not? Exactly. So let's check if this one converges. So we take the impulse response and we start to create the response itself. So what is, sorry, this should be x of t plus y, or x of n, y of n minus 1. So the first one will be
1, 1, 1, 1,
y
1.
of 1 is y of x. And now we want to have the output. See what is the filter?
1 plus 3.
1 plus 0, right? So this one equals 1. And then the second one is
1 plus 1.
that 0 plus the previous one. So this is 1. And now the same. And again and again. So excuse me. No. This is just a different example from exam. So we need to decide whether the right one is C or D.
You have a different answer for that.
Yeah, we can have-
If you use another input.
No. You can see the filter described by its impulse response. So you need to create the impulse response like this. You need to take this. Yes, this is the idea of an impulse response. You have an input of 1, so it's a great question. You have an input of 1, 0, 0, 0, and then you see what is the output of the filter. Okay? Because then you understand what this filter does to any specific point. Do you understand what I just said? Right?
Yeah.
So for every specific point, it creates this convolution.
So every time you use this array, always.
Yes.
What is
Yes. So now I want us to look at this impulse response. This is the response. This is the input, the delta. Now tell me, could we create an equivalent FIR? Why? Because it's a good answer. We don't have any 0 at some place. We cannot crop the filter, right? So could we have an approximation of the same filter? Like in the previous one that we created an FIR with a specific known error. Could we do here the same? Who says yes? Christian, go for it.
Well, the thing is, it converges to 1. So I'm thinking like, if you take any size of window, it will give you about the same information.
Okay, what do you say, Austin?
I mean, not wrong, but it's not converging as a series. The sequence converges, but the series.
Exactly. So what we need to do now is to sum it up. This is the reason why it's a really confusing example, and it is not by mistake given in an exam. So you need to sum them up, and when you sum them up, this one converges to infinity. So we don't look at the convergence. Austin, how did you call it? Not the convergence of the series?
It's the sequence is just one, and the series is the sum of all.
Series is, right, series is always the sum.
Yeah.
It's the infinite sum. This is the definition. I don't know the words in English. I know the
It's been
only.
many years, but that's how you read it.
It's this one. I mean, the one that you take all of the possible from one to infinity. But you sum all of them up.
That's how I.
Right, so this is the series. And when it's just A1, A2, and so on, this is the sequence. And we need this one to converge and not this one. Many of the sequences we have converge, but their series isn't. Okay, it's funny because in Hebrew, the direct translation of this one is this one. Right? Yeah. I'll just teach you Hebrew. It will be easier. Okay. Right. So the right answer is D, because it is impossible. Okay. So why do we have the FIR and IIR at all if some of them are just exploding and non-convergent? So FIR, first of all, we know that it is finite. The IIR relate recursively to itself. It does not mean that this is, although its name is infinite impulse response, it doesn't mean that there couldn't be any zero. Some of the IIRs has zeros at some point, okay? It is okay. But it relates recursively to itself. This is about the so here you have the basic examples that I want to show. In just a minute, I want to show you.
So that it can have zeros, that can also converge to zero.
Yes. Yes.
Now,
So,
on the name, so it's infinite because the size of that kernel can be.
yes. Yes.
While like FIR.
It has to be a fine. Yes. Right. Yes.
This part is so little, it's not converted as infinity, but what do we need? Previous question is so converted. What was the difference between?
So in the previous one of 1/2, quarter, and so on, when you sum them up, when you add it to each other,
No, but we use the same IIR, no?
no, it was a different one. There was half
Oh.
in the previous one. Okay, but if this one, it needs the series did converge. This one. Okay, so I just wanted to show you an example of how it is used, like in real life. So what we see here is that we see an input of a signal, and this one is just a simple sine signal. And then you see the signal is entered through here. And how the filter works is that within each stage, it creates another part of the filter. So over here, this is an FIR. So it starts with filtering through the part of the B0, right? And then it adds the B1 and the B2, and then you have this output, right? Is that clear? So you take this one and you just take all of it. This is really how the circuitry of the electronics works like. This is how this kind of filter looks like in reality. Okay, and then, for example, when you have this input of the sign, then the filter is the Y that you use this filter, and then you can see its output. Each one of the B0, B1, and B2. You just write them as different coefficients.
It's not one.
What are the numbers of each one?
No, the square, it's the diagonal.
The square in the diagram tells you that you had an input. Here there was a filter. You put this one here. And then you take the same input, you put it through this device. And then it goes through this filter and they are summed up. And then you take it further on, also with this device, the same input, filter, you send them, and then you have the response. Right? Okay.
Kind of like a storage device, like it holds it for one time point.
Yes,
So it's not transforming anything.
exactly. Okay. So this is, for example, with this pre B0, B1, and B2, and then we can have the same. So here is an example of the impulse response, okay? So an impulse response is that this is the input one, and then all of the zero. And then, for example, here they just simulated different for different numbers. So when you take this input response, you create this filter over here. Okay, this is how the filter looks. It's just another way to visualize it. And here we can see the IAR, and the IAR performs something else. You have this signal, and it enters here, and then storage over here, and then filter. And then you take the output of this filter and you add it here, you sum them with the next one, right? And then the output of it will be 1n. Is that more clear? For some people it is more clear, for some it is more confusing. It's just another way to visualize it. And then you can see the impulse response that you take here, the 1 and all the zeros. And this is the input that is taken through it, and then you can see how it decays, right? And this is an input one. So in a way, what we did in the previous question is that we decided what part of this decay is enough to give us about the same information. And from here, we rectified the filter, and this was equal to 0, right? So what do you think, which one of the filters is faster? Rectify is that you assign 0 from since one of the points. For example, from 30, you assign 0 to all of the responses. So you have here 1, 0.97, 0.96, blah, blah, blah. And then here at the half, you say this is enough for me, and I rectify. Rectify is like erasing everything from here on. Like in Relu, that you used a lot in the previous semester. So what do you say? Which one of them is the faster one? The FIR or the IIR? Why?
Feedback is so good, and it uses root and help.
So look again at the circuitry over here. Over here, we had only three coefficients, right? And to create all of them, look how much did we needed from this device, right? So we needed to have a big capacity of the memory and of the filter and so on. So this one takes time to filter such a signal. I mean, what does it mean to take time? That when you have the first input over here, for example, you take one, it enters the system. This is why it's called systems. And then you see that it takes really long until you have the response over here. But in the IAR, it is much faster, right? Now think again about what I said about rectifying. So over here, I have about 30 coefficients. Think how long will it take me to filter a signal with 30 coefficients? It will just take time until it goes through all of the system until it goes out, right? So the more coefficients you have, then the filter takes more time, okay? So, no, I don't want to show you this one, but this is an example from engineering that we have a comparison between IAR and FIR filters. So this is how fast they go. This is that, sorry. This is the frequencies and this is the amplitude. Yes, this is the spectrogram. And this is how this filter looks like. So in the 10th order IIR, roll-off is similar to 40 coefficients of the FIR to create the same slope, fast slope as in here. So you need only 10 coefficients for IIR, whereas you need 40 of the IIR. And if you take for both of them 10, look at the difference. This one creates a much lower quality of the filtering. Okay.
The number of coefficients
The number of coefficients. No, it's just how these systems are built. Okay. So here I gave you this example that they can be. There is a problem in my recitations. I don't know what. Okay. So this is about it for FIR and IAR, and there are only last two things that I want to show you about that. So, here there are three. I just put also here some exercises for self-learning that you can try to repeat with them about all the things that we were talking about filters. And the last thing that I wanted to talk about is the ripple problem. That if we say that we want to reduce the ripples, right, in our filter, so we go back to the frequency domain and we say that we want this ideal frequency response that we need to lower down to zero some of the responses. And then when we take it to the time domain, this is like involving with this infinite sync and we're having this ripples. So one of the possibilities is say, okay, yeah, let's just take some of these ripples and rectify them. And what happens when I rectify these ripples, I take it back to the frequency domain, and then I have the ripples back in the frequency domain. So what can we do to get rid of them? So as I mentioned before, what we do is something that we decide of instead of creating this sharp front-end change in the frequency domain, we create something that is called windowing. Okay, so windowing is what size, what part of the frequency do I allow myself to take, and pay the price of not decreasing really, really fast, but just taking this window and saying, okay, over here it's okay. And then I can reduce the number of ripples. So for example, here, these are the ripples created by a rectangular window that we saw here above. But then if you take the Chebyshev filter, which decays much more slower, then you can reduce the size of the ripples. And the longer you take the window, the ripples will be lower, okay? So window is, instead of having here the transient change, is saying, okay, want it to decay slower, and then you decide what is the size of the window that will be slower. Yes, exactly. And how do you want it to look like? From the peak frequency to the unwanted frequency. Yes. Yes. Okay, so oh, here is what I wanted to show, and this is really the last one, and then I give you a few minutes break. So the problem of I was talking about FIR and IIR and so on. So the last one that I just want you to know about FIRs is that FIRs have a problem. I don't want to go into all the math and so on. It's not really important. That they create a phase shift. You see over here, this signal over here was going through the FIR, and then it created this phase shift that you see the peaks over here are just shifted. So you have a question about this in the recitation quiz. So just read the explanation over here of how to calculate the phase shift. And what we really do is that we just crop the filtered signal to have the same phases as the one before. Okay, so we just say that we crop over here and then move it left, and then we will have again the same shift, the same phase. Okay, this is just the only thing that I wanted to tell you. And here you can see how do you calculate the size of the phase shift. Yeah.
So FIR always gives a linear phase shift?
Yes.
Okay.
This is due to the fact that it is a linear sum. Yes. Yes.
So it's saying that instead of taking a rectangular and transforming to the
frequencies, yeah, the fluctuations, right?
so you take it like this, and you don't take a rectangular, you take it more like a slowly,
Exactly.
but it doesn't give me different weights. I mean, it changes the.
Of course.
I mean, it doesn't give one sum of the points. It gives
Right.
different weights. So
Right.
it doesn't change with the frequency that we get.
It will. So some of the frequencies will not be lowered. So you need to decide where do you start the decreasing. For example, if you want to filter this frequency, so take the Chebyshev to start the decreasing much before. So you need to look at your real data, perform the Fourier transform to your data, see what is the spectrum, and only then decide how do you filter it. Okay? That's it? Okay, at 3 we'll just go on. I want to start talking about spectral analysis. And if you feel that this is too much for you, you can watch the rest of the 15 minutes at home and just have a break, a longer break. Okay? Great. This is for Sunday, no? I didn't mean to start today. This is for Sunday, and Sunday will be just my preparation day for the quiz because I'm sorry I cannot study to the quiz all of the week. Okay? And I think that moreover, it is really important that you will start by studying as a group and answering each other, and then when questions are more clear, only then we should meet. I think that during this semester, one of the mistakes of mine was that I always told you come and come and come, instead of letting you try to solve it with your friends. And then I just didn't have time to really give you the suitable answers. Sometimes you need to think about some of the answer. Like the one I sent you, it took me time to find it and to see that the calculation is right and to see that you were right if it was mistakenly doubled by 2.
Hey, Arden,
Hi.
how are you?
Doing well.
How are you?
I'm fine. Where are you?
I'm in the Netherlands. Do you know Radboud?
Why are you in the Netherlands and not here? We miss you.
I'm in a summer school for a week and then I come back.
Okay, okay.
I was
Great.
wondering, do you know which topics will be in the quiz on the 17th?
Araceli, I also don't know what are the topics for the quiz of next week. Do you know?
Yes, some information theory,
Information theory,
coding.
decoding,
Yes,
so and also discrimination, probably the ROC and so on.
that's what we have done with physics.
Okay.
Estimators
Estimators
will
will be, and that's it. So you don't have anything from the spectral analysis.
No, not frequency, but the telecast.
4 subjects? This will be on the post. Okay, I hope that I answered you, but I'm not fully sure, so
Oh,
I
I
would ask Sophia or Araceli or Noah.
okay.
one
It's
of the- their
I couldn't hear what they said because they
I
are
don't hear you at all.
I couldn't hear what they said because they are a bit far from the
They
mic.
say that they know that it's information theory,
Okay.
estimators, and probably also ROC, but they are not fully sure about ROC.
Oh, okay. Until information theory.
Yeah,
Okay. Thank you. And so this frequency and spectral analysis will be part from your
spectral analysis, no.
quiz
This will
for.
be only on the fourth
Mm.
quiz.
Okay. Thank you.
Yeah.
The last live series. What's the deadline for the project?
A week after, it depends on you. One possibility is to say a week before, and then during that week we can send you the grade. So for you it is better because then you can use the project to study for the quiz. Another possibility is to say have it 1 week after, and then you will be free after the quiz to work on to finish the project. So depends on you. I highly recommend about the first possibility for 2 reasons. First of all, it helps you with the quiz, and second, just get rid of it. Okay? The longer you take it, the longer this course will take you, and the longer you'll have the final credit. So I recommend submitting ASAP. If possible, let's think at the 17th you have the exam. And then if you want to submit before, then you need to submit by the 23rd of July. It's possible. Yeah. Why not? 23rd, and if you have an extended submission, then you can have 2 more days. Yes, why not? I think it's the best for you just to submit it. but please let me know, I don't want to start. Isa talked today about the spectral analysis. Or did he talk about coherence and cross spectrum? No. So do you remember where did he stop? At what subject? Harmonics? Okay. Okay, so we'll just have some hints. I don't know. Do you prefer to do all of this recitation by next Wednesday when you will be free of worries, or do you want to start now just a bit? Yes. Okay. Okay. So let's start just a bit, just for the motivation. So what is the idea behind the spectral analysis? Spectral analysis says that we can find few features of the data using the Fourier transform, right? The Fourier and the Hilbert. What are these features of the data? Frequency and phase, right? And now we can ask ourselves, can we see something interesting when we look at the frequencies or at the phase? And you know what, I'll just show you something nice from a presentation of mine.
I just
Tomorrow.
want to see some
Excuse me?
two features.
Two features. I'll show you just now the two features and how we like to use them in neuroscience and amplitude. Yes, this is the power of it. So I'll show you the beginning of my presentation tomorrow, and I will invite you to come and hear a very interesting talk of mine about this paper. I don't know if any one of you heard about Adam Kohn. Probably not. Very interesting neuroscientist. Okay. And what I show at the beginning is that commonly, when we want to look at two different signals, for example, two different neurons, we can relate different features of this neuron, of two neurons to each other. For example, you learn about cross-correlation. Cross-correlation tells us if there is like a specific pattern that is lagged between two neurons, right? Another possibility is to have something called coherence, that we'll see in a minute, that, for example, two regions are fluctuating in the same frequency, therefore we can conclude that there might be a relation between these regions based on the frequencies. For example, do you remember the gamma frequency that I told you about? Do you remember? This is a very important frequency in the brain that it commonly relates to high functions of cognitive, and this is probably used. Some of the theoretical studies about the gamma frequencies showed that there is probably a use of the gamma frequency to synchronize across the brain regions. Okay, like to make the information flow better between different regions of the brain. So this is the gamma frequency. And you can see over here another example, which is called phase blocking. So for example, we can study the relation between LFP fluctuations and spike in activity of specific neurons all around. Is there a relation between the fluctuations in the LFP signal? Do you know what is LFP? Yes, do you know what does that mean? Okay, low field potential. When we take electrodes and we we record the brain. You know it from intracranial, yes. Excuse me? Local field content, sorry, yes. So when we record electrodes of the brain, we can have different types of measurements. We can have a single unit, which is a specific neuron that we can see its spike in activity. Or we can have something else called LFP, which is kind of the EEG inside the brain. This is a signal that we don't know if it's a specific neuron or a bunch of neurons that are recorded. It could be either of them, okay? So far, so good. So LFP is kind of the potential inside the brain. We don't know exactly what it represents, but a few studies ask themselves, is there a relation between specific frequencies in the LFP and spike in activity of neurons? For example, we have the same electrode, and in the same electrode, some called a tetrode or a laminar, and it records from here and from here, very close by sources. And for one of them, we discovered that this one is a single neuron. And for the other, this is an LFP. Is there a relation between the signals? And then there is something that is called phase blocking, that we filter the LFP to specific frequency, and we see whether the spikes are commonly having the same phase. See, for example, here, the spikes are commonly at the peak of the fluctuation, while over here they don't have a phase blocking. Okay. So this is just an example, and of course, people found out that what is the frequency of with the highest phase locking? The gamma frequency, okay? So the gamma frequency is also highly activating and exciting for different neurons and all around. It elevates the probability to fire a spike, the gamma frequency, okay? When it's given in the LFP. Okay, so we see over here that we can use features of the frequency and of the phase to tell something about relation between different recordings, between different signals. Okay, and this is spectral analysis. Using these features to say something about the recordings. Now, I want to invite you tomorrow to hear about the next stage way of using, it's not spectral analysis, but to use machine learning, okay, for studying the relation between regions of the brain using big data, okay? So this study is about how can we do it. Okay, so you're very, very welcome. It should sound for you familiar in relation to PCA. So they offer a new way to create a dimensionality reduction. Very interesting one, and it shows some new results. So you can come here by at 8:30, or you can send me an email and I'll send you the Zoom link. And it's in our journal club of the lab, so I bring some really nice refreshments. So you are very welcome to come. Okay. And now I want to show you another example of an fMRI study. So in this fMRI study, this is where I started, so I really like this subject that is called functional connectivity. Did any one of you ever hear about this thing called functional connectivity on fMRI? Would you like to share with us what does that mean? So please tell me, what do you think that functional connectivity just means, just by its name? Yes, Christian.
From what I remember, it's having, so it's the step further from having two regions, China. It's the step further off, say that these two, they appear together in fMRI, but on top of that, they're actually.
Exactly. So this is called the functional connectivity, that we have specific tasks, that in this task, we can see that specific patterns of the brain are highly correlated to each other. So we have the attentional network, and we have the visual motor, I think, network or something like that. And then we have also something that is called the default mode network, which are regions that are just always connected to each other. It doesn't depend on the task that is performed. Okay? And this is a very, very interesting idea in fMRI. And the way that it is calculated is by correlations of the both signals, okay? Similarly to the cross correlation that we did, just with time lag of 0. We don't look at 10 seconds or something like that, just time lag of 0 across all the voxels of the brain, and then we can say something about the networks in the brain. So in this study of Muller, they wanted to try and use something else for this question. And they wanted to use a measurement called coherence. And what coherence means? For each voxel, they use a spectral analysis to find what are the main frequencies of this voxel, okay? So you see over here, these in red are the times that a stimulus was presented. Okay, the subject was sitting in the fMRI, watching and having specific stimuli, and this created like a specific frequency. And when you take off this frequency, you can see other frequencies, and each one has its own power, right? And then you can do it for each voxel. In fMRI, do you remember how many voxels we have? We have millions, right? Or something like that. A lot. Not one nor two, nor 1,000 just. Really a lot. So we can see what are the frequencies of it, and we can check whether there is a relation in the frequencies between two voxels. And when we do so we can see that, for example, in this cluster analysis, we can see over here that there was this network of connection between the visual system, also by fluctuations of the fMRI. So we can see over here, so for example, this one had this blue signal and this one had this red. So there was a high correlation in the frequency between them. So this was an example of another way to calculate the relation between regions in the brain that they offered in this paper. So I hope that now it is more clear to you what do I mean by using the features. And what we're going to do on next Wednesday is that I want to show you the exact calculations for each one of them. Because just saying the math means nothing. It's really hard to understand something. But then when you ask yourself, how is it used in neuroscience, it really helps you to better have a picture of the idea of two phases that are coherently fluctuating between two regions. Therefore, we believe that these two regions interact through this frequency. Okay? Great. So I'm here for personal questions, which are only not quiz questions, because we don't have time now to go through all of the the questions for the quiz. And at Sunday, we have a very, very long time to sit with me. Some of them are in person. It won't be recorded this time. Some of them are in Hebrew, and we also have really a long time to sit only about your questions. So until Friday Eve, I need the presentations to be ready so that during Saturday I can start prepare to the class. Okay. And that's it. Be well.
Thank you.
You're welcome.
Bye, thank you.
You're welcome.